Good morning, everyone. Nice meeting you. Welcome to Costa Rica. My name is Rolando, and I'm going to talk to you about seismicity, seismic code aging infrastructure of Costa Rica. I have plenty of slides, so I will get into business right now. A few facts about Costa Rica. Population, 5 million people. Area, 51,000 square kilometers. Just to give you an idea, Florida is 3.6 times the area of Costa Rica. And we are 3.3 times greater than Connecticut. So we're winning up there. 7 provinces: Guanacaste, Alajuela, Heredia, Limón, Cartago, San Jose, and Punta Arenas. Number of volcanoes, 200. 5 of them still active, and tomorrow we're going to go to one of those. Highest mountain, Chiripo Peak, 3,820 meters. The highest volcano, Irasu volcano, that's the one we're going. Average temperature, 26 degrees average at the coast, but it gets hotter. Central Valley, 20 degrees. And at high mountains, 10 degrees. So please bring your coat tomorrow. National parks, 28. Just to give you an idea as well about population in main cities. San Jose, Alajuela, Cartago, Heredia. Here, Alajuela, San Jose, Cartago, Heredia. Around here, we got around 1 million people. Other cities with less population that are important: Limón, we're heading to Limón on Saturday. Golfito was not included there. Liberia up north, and Punta Arenas here. So that's important in order to understand what is coming. The Pacific Ring of Fire. You know that Costa Rica is an earthquake prone. That earthquake is a land of earthquakes. And the reason for that, as you might know, is we are in that subduction zone. A subduction zone where 3 plates interact: the Coco plate, the Caribbean, and the Nazca plate. And as part of this workshop, you will be traveling, well, Eric and Richard, you will be traveling around this ring of fire. And the reason for that, subduction zone. That's what creating most of the earthquakes around the world. And Costa Rica is in one of those zones. So we look here, and we can see the boundary between the Coco plate and the Caribbean plate. And as you can see, the subduction is happening. There's a collision with the Caribbean plate that is generating some fracture on this plate, which creates our volcanoes and also creates local faults. And in Costa Rica, we have plenty of them, local faults, because of that subduction. 79 has been counted at the National Seismological Network of the University of Costa Rica, and there are more according to other recent studies. And the following faults have the potential to generate an earthquake of equal or greater than 6.5. And they're shown in this map. Look, I was showing you before the population, where it's concentrated, and here we have several faults. 1, 2, and 11. The Agua Caliente, the Alajuela fault, and the Navarro in Cartago. We also have a fault, an active fault here in Limón, and there is also active faults local faults here in Golfito, and many along the Pacific coast. So we're in an active zone where earthquakes happen often. So just to give you an idea what had happened in the past, we can see here major earthquakes. I have gathered these earthquakes, and I want to explain to you a little bit about each of them. By the way, that's Limon in 1991. Did you know that in 1910 we had a San Jose earthquake on April 13? Location southeast of San Jose, magnitude, I don't know how they got that information, 5.9, 7 in the Mercalli intensity scale, which is around 7. Very strong, considered according to the modified Mercalli scale. Death unknown, victims 300 plus. 150 houses destroyed, 23 buildings with severe damage, churches, schools. This is San Jose. Essentially, 3 weeks later, we got Cartago, May 4th, 1910, 7 p.m. at night. The earthquake happened, and nobody knows until the following day what happened. No lights, nothing. Magnitude 6.4, max intensity 8, shallow, dead and injured 700 people plus. Many buildings partially damaged by the San Jose earthquake collapsed as well. The previous one I explained. There was a report of the collapse of a bridge crossing of the Agua Caliente, crossing the Agua Caliente River. Those are all pictures about what happened at the time. Unreinforced construction, adobe. So because of those earthquakes, the municipality of Cartago at the time, with the approval of the president, Ricardo Jimenez, they approved urban construction regulation where construction of adobe, using materials like adobe, bajareque, calicanto, or stone was prohibited. This is key. Key in the sense that we started to prepare ourselves as a country to earthquakes to come because we prohibited this kind of construction, which has shown from those earthquakes that they didn't work well. That kind of construction didn't withstand the forces of nature. And because it has shown in other countries, Central America and South America, that they don't work. Tilarán earthquake, April 14, 1973. Up north, magnitude 6.5, death 23 people. Collapse of unreinforced concrete construction, houses, and damage to buildings. Many roads were closed by landslides. Golfito earthquake, April 2nd, 1983. Death, 1 person. Severe damage to 25 houses, with 44 houses with minor damage. There was a collapse of some buildings, including the municipality building. There were reports of settlement of approach slabs in several bridges. Cobano earthquake, March 25. Victims and injured, no reports. 79 buildings and 32 houses damaged, 8 of them completely destroyed. The port of Caldera, which is around somewhere here, was damaged, and the breakwater as well. Damage to the pier and the breakwater. There were reports of liquefaction at some coastal areas. Limon. This is a big earthquake. It had a lot of impact in our country. 1991, April 2022. Here's the epicenter, 10 kilometers deep. 651 Costa Ricans were injured and 1,000 in Panama. Victims, 48 in Costa Rica and 79 in Panama. Lots of damage everywhere. And if you want to know what happened there, there's an earthquake spectra which summarizes what happened over there. The Limon earthquake caused damage in an area of 8,000 square kilometers, 80% in Costa Rican territory and 20% in Panama. Damaged homes, 7,000. Collapsed houses, 4,000. Lots of damage in vital lines, including roads, railways, bridges, ports, aqueducts due to liquefaction. In Costa Rica, it was necessary to rebuild 309 km of roads. Just to give you an idea what happened with the bridges. Liquefaction, lateral spreading. Not just bridges, buildings. Hotel Las Olas. Soft story together with some short columns, sheer damage in the columns. In fact, when we go to Limon, probably we'll see the ruins of that building. I think they're still there. And it's very close to the restaurant we're going. Cinchona earthquake, January 8, 2009. 6.2 magnitude, intensity 9, which is considered violent. 4.6 kilometers deep, 27 victims. A lot of destruction to homes, schools, churches, businesses, and industries. It was reported that most of the damage to homes are those that are not built to the code, today's seismic code, the Costa Rican code. If those buildings would have been constructed according to the code, we call them informal construction, done by local people. If they would have followed the code, probably that damage would have reduced substantially. But that's a problem we have here in the country. Of course, adobe and bajarek, as I said before, is not used in Costa Rica. It's culturally not used at all. And it's prohibited. Many landslides affected homes, roads, and factories, and even a hydroelectric plant, which suffered severe damage. So to give you an idea, landslides were huge, all around the area. The town of Cinchona, which is the name given to this earthquake, has to be relocated to another place. So we have some damage of informal construction without an engineer involved. Samara, this is the last one. Again, I pointed to victims, 2 victims, 78 injured. 60 houses destroyed and 1,000 were damaged. There was a damage to a hospital. What do we expect from a hospital during an earthquake? We don't want damage on a hospital. Well, we actually did have damage to this hospital here in Punta Arenas, which has been retrofitted in the past. What is going on? Roads were affected. Who have been in an earthquake? Magnitude 6. 6. From the US people? In India, you said? In the US? Okay. Well, let's have a look and see what it looks like. This is Samara in a supermarket. I just found this video. I thought it was interesting. That's the same lady we saw before. So don't panic. Let's get out of the, you see, there's a culture. Looks like the wine bottles are not coming down. So who wants to be one of those? Why did I show you this? Now look what has been happening in Central America with regard to the consequences due to earthquakes. For instance, Managua, 1972, between 5,000 and 7,000 people killed. Magnitude 6.5, local fault. Guatemala, 1976, 23,000 people killed, 80,000 injured. San Salvador, 1,500 people killed. Pacific coast of Nicaragua, 1976, 120 people killed, lots of homeless. And then El Salvador again in 2001. Many of these people, 1,150 people killed, were killed because of a landslide. So if we compare this to what has happened to us in the past, it's nothing. It looks like we're doing something good. So a little bit now, what have we been doing? Our seismic code, to understand a little bit, in 1971, the School of Civil Engineering here at the university started to teach earthquake engineering. They started to see that that's important. We need to get into that. And that was in 1971, but then two earthquakes happened, the Managua of 1972 and Tilarán of 1973, which I explained you a little bit before. Those events triggered the drafting and implementation of a national seismic code. A national seismic code that was drafted by a commission of professors of the School of Civil Engineering and practicing structural engineers who received the support of the Federated College of Engineers and Architects of Costa Rica. Because of that, okay, so do you ask what we were doing before that? Looks familiar? That's the recommended lateral force requirements from the Seismology Committee of the Structural Engineers Association of California. The Blue Book, that's what we were using before 1974, which was the date when we had our first own code. So we were using something useful. We were doing simple elastic analysis of structures. Oh, I couldn't finish that. So 1974, our first code, 55 pages long. Cutting edge aspects were included. Consideration of ductility, dynamic analysis of modal superposition, control of inelastic displacements. And this is what we got in there. The seismicity was considered uniform, one seismic zone. We had two acceleration response spectra for alluvial and non-alluvial soil. And the peak ground acceleration that was established in this code was 0.17 g for alluvial soil and non-alluvial 0.15 g, ground acceleration. So we use this spectra in order to calculate our seismic coefficient directly from that spectra. Then it came the 2006 code, the 1986 code. Look, from 1974 to 1986. Took a while to get another updated version. 127 pages. So there were some improvements done to the code. Here, in the previous, we just have one seismic zone. Here we introduce a map with ground isoaccelerations for the first time, considering the first seismic risk study of Costa Rica. Aspects introduce general guidelines for prefabricated concrete systems, specifications for 1- and 2-story housing. We found that we have to specify more on this area, and design specifications, more information for different structural materials. So this is what you will find as our hazard map with accelerations, acceleration curves. We look now at the spectra as a dynamic amplification factor. So we multiply the maximum acceleration at the site times this dynamic amplification factor, and we reduce the maximum acceleration by 0.8 in order to convert maximum ground acceleration to effective acceleration. In the third seismic code, this had 272 pages, so it is increasing as well. Now we move the hazard map moves from isoacceleration curves to seismic zones. We introduce nonlinear analysis as an alternative to the usual linear, static, and dynamic methods. And in parallel to this code, we also publish a commentary to the code for the first time. This is what we see now. Zoning, free zones, zone 2, 3, and 4. We have a dynamic spectral factor, which is like a normalized spectrum. We now, if you remember, the first code, we had a ground acceleration of 0.17. In 1986, the peak ground acceleration was 0.31. It did jump quite a bit. And here, I estimated from the acceleration, from the effective acceleration that the codes are providing me now, based on the zone and on the type of soil, for San Jose, I'm estimating a peak ground acceleration of 0.38. So it went from 0.17 in 74, 86, it went up to 0.30, and in the code of 2002, it jumped to 0.38 G. This is a gross assumption that I'm doing here in order to compare the accelerations between the different codes. Not necessarily is the right approach, but is valid, I believe. So the seismic coefficient I obtained with the peak ground, the effective acceleration, the effective acceleration, the importance factor, which is a factor that is introduced, the normalized spectrum, the dynamic spectral factor, divided by the overstrength, which is another parameter that was included for the first time in our code, following what has been done in the US as well. And finally, our current code, the seismic code of 2010, got even bigger, 400 pages. In fact, there's also an updated version in this version was updated in 2014 for improvements. What we found in this, what we did in this one is modify the seismic zoning map. We did some modifications to the importance factor. We updated some of the requirements for structural materials, and we revised our simplified design method for housing, and also some of the structural details. And the reason for that is based on experience with earthquakes that have happened in the past, has shown us that we had to improve some structural details. So this is what we see. If you remember the previous zoning map, well, look at this one. I'll show you the one before. Well, this zone, the zone number 4 just covered these 2 peninsulas, but now in the 2010 it covers this part of this area as well. Can you see it? Cover a longer. Remember that we have this subduction zone, this area. One thing you find out as well, that the effective or peak ground acceleration wasn't modified. It remains the same, essentially. So that gives you a brief introduction to how we have been working on our seismic code, and I heard that probably this year or the following year we will have the next version, where it's expected to include seismic isolation and probably dampers as well. Yeah. So if you look at the building landscape of San Jose, you will see it's quite a flat city. But we see some, for us, tall buildings. In comparison to the States, of course. This is National Stadium, and some tall buildings scattered around. This is our Central Park, La Sabana. And of those low-rise structures, I want to tell you what do we use for construction. We use concrete block masonry, which is very popular. Reinforced concrete for medium-sized, big, high-rise buildings, we use reinforced concrete. But some housing is being built using this only reinforced concrete lately. Precast concrete walls made with horizontal or vertical panels. These are being used for low-income housing, very popular. If they are built properly, they work very well. We also have, and that's very popular. This one here, panels of expanded polystyrene surrounded by steel wire mesh. This has gained a little bit of a popularity in recent times. It's not that popular, but is gaining momentum. Then we have steel structures, industrial. It's essentially in industrial buildings. But high-rise buildings, very few of them. I can recall probably 3 or 4 that I have seen around the city. Wood framing, as we do it in this country, it was used as a low-income construction in the past, not necessarily today. More is the precast construction that I show up above. And then we have some leftovers with regard to adobe construction. So timber framing, steel framing is not used, well, is not very much used in this country, which is very popular in the US Canada, Australia, New Zealand. Now let's look at the building scenario. Here I have a list of buildings of more than 40 meters tall. And I have put them by decade. And these are all the buildings. Let's look at 1960. These are the buildings that were built in that decade. Just those two buildings, according to my research. This is a office building. It's public, telecom and electricity sector. And the other one is just also a public building from the health sector. 46 meters tall, 50 meters tall. So, which code did we use to design this? The Blue Book, probably. What acceleration did we use for that? Probably a very low one. If we see what we use in the first seismic code of Costa Rica. It's going to be retrofitted soon, but it has taken quite a while to do it. 1970s. I believe these are all the buildings built in that era, in that decade. There's a private building, telecom, insurance, office building. This is a health sector office building, and this is a private building. 43 meters, 58, 61, 70 meters, 52 meters. 1970. Here are the years of each one of those. Blue Book, probably Blue Book. Maybe here we started with the first code of Costa Rica. '80s. Hotel. When it started, it was a Playboy hotel. Yeah, we had a Playboy hotel. Not anymore, but it still exists. A bank, 80 meters tall, used to be the highest building in the country. Holiday Inn Hotel, private, oil industry, office building, and the government controller building. Interesting one. So, looking at if we recall our seismic codes, the code of 1974, 74, probably 74, and this one's maybe 86. So there was a difference in accelerations between one code and the other, almost twice. So how are these buildings at the moment? '90s. I missed some buildings here, but they're not. I took them out, but there are not many. I can put them in one slide. The high buildings more than 40 meters tall, 40 meters. So this is very close. This is very close from here. When you go back to your hotel, you will see this. It's just in front as you get out of the university. This is an office, private. Look, residential. We're starting to see residential in 1996. Office, 1999, 1999 office building. All of them using the code, designed with the code of 2000 and 1986. Now 2000, we started to see residential. Now we move into residential, private construction, hotels. The government is not building any more high-rise buildings. Now is the residential construction, the private sector who is investing. 2006, 2008, now we are designing using the code of 2002. And the last decade, this is the tallest building in Costa Rica, 100 meters tall, One is 97, the other one is 100. Residential, office, building. But those here are have been built recently, and all of them are from the private sector and are residential. So we're going high-rise. So I put you in perspective these buildings and the situation with the seismic code to see that our infrastructure is aging. We have to retrofit our structures. What are we going to do from now on with regard to building new structures? Are we still building as usual, or we could be thinking about implementing new technology? What about bridges? This is something very important in the work we do here at the university. For instance, all the bridges are responsibility of the Ministry of Public Works and Transportation. Historically, our Ministry of Transportation, MOP, has specified for bridge design the AASHTO standard specification for highway bridges, American standard. And more recently, the AASHTO RFD. And for bridge construction, the standard specification for the construction of roads and bridges on federal highways projects, the FP. However, from 2013, we published for the first time guidelines, not a code, but guidelines for seismic design of bridges. And if you go in, you will find out that those guidelines are based on the AASHTO LRFD. And at the same time, also a year later, we published a commentary. So if we look inside, we will see that we have used the same zoning as for buildings, but the approach with regard to the spectra has changed, because now we construct the spectra as is done in the US as well. We have defined some spectral seismic coefficients that depends on the soil type and also on the zoning, the seismic zoning. The difference with buildings is that the return period to design bridges is 1,000 years, which is, in case of bridges, in case of buildings, we use 475, which is in sync with what the US is doing. And because the return period is bigger, we expect to have a larger ground acceleration. So based on the information that is provided, the ground acceleration, the maximum ground acceleration is 0.45 G for bridges. So for building is 0.38, for bridges is 0.45, as is today. So I put a roadmap just to put you in perspective. San Jose, route number 1 goes to Nicaragua. Route number 2 goes to Panama. Here. Route number 32 goes to Limon. And route number 27 goes to the port of Punta Arenas. Those are the main routes in the country. And what is going on with bridges? We have found, the government bridge data shows us that there are 1,500 bridges, of which many of them are, 64 of them are made with concrete and 32% of steel. The length of the superstructure, 69% of those are girder bridges. And 12%, which is the second, rigid frame bridges. We see that the arc bridges, suspended bridges, cable stay or suspension bridges are few. So most of our bridges are girder bridges. made of concrete, with a length of about maximum length. Most of them are around between 6 and 50 meters long. Most of them are located in the province of Alajuela, followed by Punta Arenas, Guanacaste, and San Jose. And the condition, according to this government data, is 62% are in regular condition and 34% are deficient. They only have free grades to tell us the condition of the bridge. Damages, most of the damages are, for instance, in railings of steel. The expansion joints are in very bad condition. And issues, we found a lot of issues with steel bridges, not much maintenance. But we believe here at LanammeUCR that this grading system is not good enough. We are trying to show the government that what they've been doing is not properly done. So we have another system, and we have suggested another system to grade our bridges from 1 to 6, from satisfactory to unacceptable risk. And because we're going to Limon on Saturday, we will be traveling along the national route number 32. And you would like to know what kind of bridges are we going to cross, don't you? How are they? So here we see that in an alarming situation, 50% of the bridges, we found that 50% of the bridges are in an alarming situation. These are 34 bridges we're going to cross between Rio Frio and Limon. 56% of those 34 bridges are in serious condition and 29% are in deficient condition. As you can see, most of the bridges are in alarming and serious. Whoa. You want to go? Yeah, it's good. Let's go. Let's go and see them, because we're gonna have a look at some of them. One in particular, the Rio Chirripó bridge, which is in very bad shape since 1991. You remember the earthquake of 1991? Since then, that is the condition of the bridge is as you will see it on Saturday. But the good news is that we are doing improvements to this road. And we will see what is going on as we travel to our destination. This road is a 2-lane road and will be extended to a 4-lane road. So works have started. These bridges are going to be rehabilitated, and new bridges are going to build parallel to the existing ones. Some of them will be demolished because they are in very bad shape. Others will be rehabilitated. So look at the bridge typology from 1940. I have put it in this again by decade. Let's see, for instance, in the 1940s, we used to build trusses, truss bridges, and you have seen it yourself in the US. This is a truss bridge, 61 meters long. This is the 1940s. This is a truss bridge combined with bridge steel girders. And 1950s, we have steel girders, we have reinforced concrete girders. But what is interesting about this is, what did we use to design them? ASHO 1941. Live load HS 1544, which is the 24-ton, 54 kips. And this is for design, and for construction, the Federal Project 41. these bridges, as today, they need to be retrofitted. And they still exist as they are now. But we're not going that way, okay? Now we look at the 50s. Now we're using ASHO 1953 and the live load HS1544. There's no mistake here. If people who doesn't know about design of bridges, ASHO means American Association of State Highways officials, and that name stays until 1970s, and then it was the transportation, the ASHTO, the T was added from 1970. One important thing about those bridges, thank you to the support of the US government. There's some placard installed on the railings of those bridges that says, for instance, in the case of the Barranca River, built together by the Republic of Costa Rica and the United States. This is a drawing of those bridges where it shows the signature of a Costa Rican engineer and probably the design done by the US. So thank you very much. Because many bridges were built with the aid of the US, especially for Inter-American road that goes from Nicaragua to Panama, route number 1 and route number 2. 1960s, Chiripo, we're going to see this bridge on Saturday. We use ASHO 1965. Now we increase the live load to HS20. So we designed it for 32 tons. Rosales River, reinforced concrete. Reventazón River in the 70s is a reinforced concrete box girder. And now here we have, this is post-tension, this is pre-stress. So look, pre-stress started in the 1970s. Concrete. 1980s, it's very nearby, one of the first overpass in the country. When our national team, soccer national team wins, this is the place we go and gather and celebrate. That bridge is a monument when we win. So we use ASHTO 1977. And now we're starting to see our own specification for bridge construction and roads. The first cable stay bridge, donation from the Taiwan government. They use ASHTO 1996 and the ASHTO construction of 1990. This is route number 32, the Stiero Bridge. No, this is route number 27. The Stiero Bridge, weather and steel girders. ASHTO 1992. Almost done. And then in 2000, we increased the live load to HS2044 plus 25%, 40 tons. As per the US. Construction specs, our own, which is based, this one is based on the FP specifications. And in 2010, we started to see bridges that had been retrofitted in the north part of the country, in route number 1, because we have expanded the route from 2 lanes to 4 lanes. So we have built a new bridge, and we have retrofitted the old bridge. So the old bridge was built in 1955, steel girders, and the new bridge, reinforced double T pre-stress girders were used as superstructure. Here, as you can see, ASTO 2002, HS 20 plus 44 plus 25%, and we are using our own specification for design. And this is my last slide, where I show the future. This is the route number 257, the overpass to access the container terminal of Moín. That is in Limón. We are heading that way. Our bus is going to go this way. And we go in there to the terminal to have a look at it. But what is interesting about this is that this overpass is using friction pendulum bearings. This is 2010. Here we have another case for the extension, the increase in the number of lanes from 2 to 4, which is going to happen in Limón as well, but in between, in route number 1, north of the country, we find that in the intersections of the cities of Liberia, Cañas, and Bagaces, we have other new overpasses. And these ones have been built using high damping rubber bearings. And for that, we are using the guidelines for seismic design of bridges, and we are using our own specification for bridge construction. So with that final slide, I want to thank you for your patience, and I hope I give you a perspective of what you find in this country with regard to infrastructure. There are a lot of things we need to do. We need to improve. I believe we need to use new technology. Here at the university, together with Sergio, we are working towards the implementation or creating capacity in this country to use seismic dissipation, energy dissipation devices in buildings and bridges more often. And for that purpose, we believe that we have to improve our code. We have been in this discussion with the seismic code members about the introduction of base isolation and dampers for its to be specified in new chapters of the code, and they are totally in agreement with us. So in the near future, we hope that we will be going that way. So I believe that this workshop is going to be very useful for us, and hopefully useful for all the people from the US. Well, thank you very much.